Hello everyone, welcome to EV charging system configuration, operation and control. Myself is Dr. Shailendra Kumar, Assistant Professor in the Department of Electrical Engineering, Indian Institute of Technology, IIT Bhilai. So, under this particular title we will cover AC-DC converters with power factor corrections for EV charging. So, content for this particular topic is introduction, classification of AC-DC converters, comparison of AC-DC rectifier topologies, what are the kind of rectifier topologies which are available, analysis of DC AC configuration with PFC. So, here we will see one topology and we shall try to analyze the ripple current as well as other parameters which will be estimated for that particular topology, and then last we will discuss the summary of the lecture. So, it is observed the charger which we have right now, it draw very highly distorted currents. So, basically there are two types of loads, I would say power electronics based loads. So, suppose you have a rectifier which is converting AC supply into DC supply and immediately you have connected one inductor. In other case, we have rectifier and immediately you have connected at the DC side a capacitor. So, we have two types of load, one is a stiff voltage load and another is a stiff current load. So, if we have rectifier followed by RL, that is comes under the category of a stiff current type of load. However, if we have resistive load along with the capacitor, then this type of load counted under the category of stiff voltage load. Generally, in case of charger, here one can see we have capacitor, then our rectifier is, before this capacitor we are using one rectifier which is converting AC into DC and immediately we have one capacitor. So, most of the time in electric vehicle charger we have this kind of configuration, and if you observe the waveform at the input of the discharge rectifier, it draws peaky current. It is discontinuous for a particular period, then depending on the input and output voltage, there is certain conduction of the devices and then we will get the peaky current in positive half as well as in the negative half. So, the total harmonic distortion is around 70 to 80% for these type of configuration. Therefore, it is mandatory to do the power factor correction along with these type of topology. So, one aspect like we are converting AC power into DC, but this power factor correction unit is also important whenever we are going to convert this AC supply into DC. Therefore, the uncontrolled converter have been used up till now for the rectification of AC supply mains, but nowadays people are going for a bidirectional charger and they are using control devices. So, apart from conversion of DC to AC as well as AC to DC, they can address the power factor correction. Now, if it is observed, an uncontrolled rectifier has an input harmonics as I told you, around 60 to 70%, and this creates the power quality issues at the grid, and it is not economically advisable. Therefore, people have put some standard to address these challenges. So, according to IEEE 519, IEC 6100032, harmonic spectrum of the grid current must be less than 5%. They have certain limit, it should be less than 5%, and in Indian grid conditions there is voltage fluctuation around plus minus 15%. So, our charger should be able to operate under Indian grid condition, because there is certain sag and swell in the voltage. So, it can compensate this sag and swell, as well as it should address the harmonic content which is present in the current. So, what are the consequences of these kind of topology? Unadvisable tripping of charger due to unstable Indian grid condition. Whenever there is voltage fluctuation, the devices may got tripped, and which may interrupt the charging from grid to vehicle, and there is improper functioning of chargers which may pose a serious threat to the EV and reduces its life. So, depending on the converter used in the charger, switching losses increased with the number of switches. And if you have two stage charger, suppose we have AC to DC and then another DC-DC stage is utilized to control the DC bus voltage and battery current. So, there are two stages, both the side we are using switching devices, and they may increase the total losses. So, AC-DC converter are required to integrate with the smart electric vehicle charger, that not only provide the charging facilities, but also help in fast charging, mitigating harmonics of the supply system and power factor correction. So, generally what we used to do, if there is inductive load, the power factor is lagging; if there is capacitive load, power factor is leading. However, here the power factor is derived whenever we have power electronics based load. Power factor is not only depending on these type of loading, but it also depends on the power electronics load. Means, suppose we have diode rectifier followed by RL or RC, the power factor definition will be changed to fundamental power factor, that is known as displacement power factor, multiplication of distortion factor. And this distortion factor, whenever we have these power electronics AC to DC convergent devices, the distortion factor could be 0.9 or 925. So, even though your fundamental power factor is unity, the overall power factor may reduce to 0.9 or 0.8. So, therefore, whenever we are having these kind of load, there are harmonics, they may create some distortion, and these distortion directly reduce the total power factor. So, conventionally AC-DC converters have the demerit of poor quality in terms of injected harmonic currents. It may be there is voltage distortion, poor power factor, as we discussed, this distortion factor reducing our total power factor. Slow varying ripple DC output at load end, we may, if we have single phase topologies. So, single phase instantaneous power is oscillating with second harmonics component, sin 2 omega t or cos 2 omega t. So, what we have to do, we will realize one second harmonic ripple is reflecting at the DC bus, which we need to address that also. low efficiency, large size of AC and DC filter. To filter out these second harmonic DC component as well as higher order harmonic component at the AC side, we require large size of AC and DC filters. And sometime people are also putting filters which are tuned for a particular frequency. So, the solution of all these type of problems, if you are integrating a charger with the electric vehicles, we have to integrate improved power quality converter in it. So, that apart from AC to DC conversion, it can also take care the power quality issues, power factor. So, switched mode rectifier is the solution for above problems. Development. Now, the question is how we can develop these type of converters or these type of switched mode rectifiers. So, as we know, MOSFET can be switched on at very high frequency in the megahertz level, but the power level of MOSFET is restricted up to some extent. Generally, MOSFET people are using for low power applications. However, we have other devices, insulated gate bipolar transistor IGBT and other is gate turn off thyristor GTO. So, IGBTs are utilized for medium power applications. However, gate turn off thyristor people are using for high power applications. So, IGBT frequency around 10 to 20 kilohertz, these devices can be fired or switched on at 10 to 20 kilohertz, and here you can see one stack at the white one that is representing a stack of a IGBT, where two IGBT are clubbed and we make a leg. So, in generally 3 phase or single phase, you will find out there is one leg, and in one leg, I mean there are for 3 phase there are 3 legs, but in one leg there are 2 number of devices. So, both the devices we have mounted in a particular stack and we make this IGBT module. Upper side you can see the MOSFET which has 3 terminal, and so these type of devices are used to make these improved power quality converters. The another development which requires improved control approaches. So, here people are using various adaptive control, closed loop control, so that they can address the DC bus voltage regulation as well as regulation of battery current if we are talking about the EV applications. Nowadays, people are also using some advanced control technique, so that the steady state as well as dynamic responses are improved. Control is playing major role for switching on and switching off these devices. Varying configurations, we may consider various configuration. We can use 4 number of devices, 2 number of devices along with 2 diodes, like that we can develop various configuration. Revolution in microelectronics, sensing devices, suppose we have ABB make sensor current and voltage sensor. So, various in closed loop operation, various parameters are there which we need to sense and provide the closed loop operations. Then we have high speed and high accuracy microcontroller and DSPs, digital signal processor. So, the speed of microcontroller is important here. If your control is lengthy, and so the time of microcontroller will be increased. So, what we have to do, we need microcontroller which can respond very quickly. Even though length of the simulation or length of the code which we have the control which you have developed in form of code or in form of MATLAB software, people are using to develop this control using block diagrams. Using MATLAB library, they are developing these controls, some block sets are there and they are developing these control. So, if length of the simulation or length of the code is large, so these we need some high accuracy as well as high speed processor, so that these processor can quickly respond. Now, IPQC technology, it is a mature technology for the AC to DC conversion, which can address reduced harmonic current, high power factor, even though distortion factor is low. So, they can improve the power factor close to unity, low EMI and radio frequency interface at input of the AC mains, well regulated and good quality DC supply they can provide to the battery, so that there is no any kind of harmonics or ripples is injecting to the battery. Rating ranging from fraction of watt to several hundred kilowatts power rating, so that we can design a charger from low power to the high power. We can design level 1 charger, level 2, level 3 DC fast charger using these devices, using these IPQC based improved power quality converter based configurations. Now, classification, they can be categorized as a unidirectional and bidirectional power flow. Power flow could be only in one direction from grid to vehicles, as well as these devices are also available where they can work as they can work in power flow. They can use these devices in both the direction. Power flow could take place from grid to vehicle, grid to battery, as well as battery to grid, and they have been classified as depending on the type of converter as well as depending on the number of supply phases. So, for example, unidirectional boost converter is used in battery charging, switch mode power supply, low rating adjustable speed drives in fans, air conditioner, etc. Other category of IPQC for high voltage and high power applications, multi-level inverters, multi-pulse converters, right. So, we have these converters which could be used for high power applications. We can develop DC fast charger with the help of these multi-level converters. So, the classification has been done on the basis of topology, type of converter and supply based. So, here we have supply based classification. So, supply is available in form of single phase and 3 phase, and in single phase we may have unidirectional where power is going from grid to vehicle only, and then we may have bidirectional. So, nowadays the vehicle to grid technologies is very popular, and bidirectional converter are playing vital role for injecting battery power or supporting utility grid under peak load demand. So, for that operation bidirectional converters could play a major role. Similarly, we may have 3 phase, we wanted to make a semi fast charger. So, we can use 3 phase supply as there is some restriction from the single phase side. 3 phase supply could be classified again in similar manner as we have seen in case of single phase, unidirectional, bidirectional. So, here this is the classification of single phase AC DC converters. It is having unidirectional and bidirectional. Under unidirectional we have boost converter, buck converter, buck boost and multi-level. Again we can use boost buck, buck boost, multi-level for bidirectional also. Classification of 3 phase AC DC converter. So, in similar as we have seen in case of single phase, they could be classified as unidirectional, bidirectional, and then we may have, depending on the applications, we may have boost converter, buck boost and multi-level and multi-pulse converters. So, we have converter based classification. We can use dart bridge rectifier using step down chopper. So, that is basically a buck converter. We may have dart bridge rectifier two stage system, two stage charger is there. Initially we have diode bridge rectifier, after that we may use buck converter. We may use boost converter along with the diode bridge rectifier, and we may use step up down, that is the buck boost, right. So, this way we can classify for unidirectional, and for bidirectional we have some advanced controller like push pull, half bridge and voltage source inverters, voltage source converters as well as current source inverters are there. And these BSI, they may have 2 level bridge based, H bridge, 2 level, and then people are going for a higher level 3, 5 or other multi-level inverters. Similarly, CSI are also classified in this manner. And similarly we can also classify these DC fast charging, which has 2 stage AC DC rectifier and DC DC converters, and these can be classified in this fashion. So, first we will see the single phase classification. Here we have various type of first we will see the unidirectional topologies with single phase supply. So, here we may have battery and LC filter will be requiring to filter out the harmonics. So, here it is the first topology of unidirectional single switch buck converter. So, after this AC supply we have diode bridge rectifier and one LC filter is connected. After this LC filter we may have second stage, and this second stage has a buck converter. So, after capacitor immediately one switch is there, and using switch, diode and one inductor we are making a buck converter, and further the power is transferred to the load, which is battery in case of electric vehicle. So, this way we can make the unidirectional. Now, so we have buck type of rectifier is a power converter used in electric vehicles, charging system to regulate the output voltage and ensuring it lower than the input voltage. So, there are various key feature like wider voltage control it can provide, inherent interest free startup, overcurrent protection, and it could provide power factor corrections. Common topology of buck type rectifier, we may have various challenges also like parasitic capacitance and voltage regulation is the big challenge. So, now suppose we require higher voltage at the battery side. So, we can go for the boost converter. Here we may have single phase unidirectional boost converter. So, the first stage is same, it is using DBR, diode bridge rectifier. However, at the second DC DC stage you could find out we have used one inductor, we have replaced the position of switch as well as inductor and diode. So, now inductor is coming directly after this diode bridge rectifier, and then we could have switch and the diode. And the control for this we have also given closed loop control. So, we have sensed this VD voltage at the output side, load side, and it is regulated. So, suppose we require 700 volt at the output side, we can put the reference as, we can choose the reference as a 700 volt, reference is chosen as 700 volt, and we have compared with the sensed voltage. And one controller is required to regulate this voltage, that is simple PI controller is there, and this error further compared with the sensed inductor current, and we have also measured the inductor current which is given to the current mode control, which could be some hysteresis control or some PWM we can utilized, and we can switch on this particular device. Unidirectional 2 switch boost converter where 2 diode and 2 switches are utilized and power can be fed to the load. So, this topology was symmetrical. We may have unsymmetrical topologies where one leg has this switches only and one leg may have the 2 diodes. So, this type of, if we are connecting these devices in such a manner, then this topology is known as unidirectional. Unidirectional 2 switch interleave boost converter, whenever power level at the output side is very requirement of power level at the output side is very high. So, we may connect in interleaved manners. So, the current could be shared, right. We have suppose I s current is there. So, I s can be bifurcated into I s 1 and I s 2. Total current could be I s, but it is shared by these interleave boost converter. We may have other topologies, single phase VSI full bridge bidirectional boost converter. Here we have 4 devices and then followed by a capacitor, and then it can interface with the battery of the electric vehicle. Similarly, we may have 3 phase topologies if you are going for a high power type of converters or high power charger, semi fast charger. So, we may have this kind of configurations. So, it is also a single phase, as you could see we have voltage source AC supply and it is connected with 2 leg, positive and negative, it is connected 2 leg. However, we can use one midpoint from the capacitor and it is connected with the 3rd leg of these devices. So, bidirectional 2 switch half bridge, it is also popular topologies. So, instead of having 4 switches, we can utilize in one leg 2 capacitor and 2 devices. Using 2 devices, we can also make a this type of converter. We may have 4 devices which we have already seen, and then we have this bidirectional 6 switch full bridge boost converter. We may have bidirectional 3 level converter, where extra apart from 4 devices we have used another combination of 4 devices and it is connected to the midpoint of the capacitor. Then bidirectional 3 level diode clamp converter, we can go to the multi-level converter which are categorized as the diode clamp, fly back converters. Now 3 phase, so 3 phase could be connected using 4 devices and another supply phase, it is connected at the midpoint of these capacitor. We could have 6 devices and all 6 devices are connected in such a manner, they are forming 3 leg converter. So, we have various key features, purpose and definitions, applications, high power EV chargers, semi high power like AC, and people are also using up to some extent for DC fast charging, and it could help for regenerative braking system. We have bidirectional 6 switch boost converter, 3 leg VSC here. So, neutral of this is connected. So, this topology is known as basically 3 phase 4 wire, where we need to mitigate the neutral current. So, 3 leg is connected through the 3 phase supply and neutral wire is connected to the midpoint of these capacitor. Instead of using capacitor, we can utilize in 4th leg also we can utilize 2 devices, and it is the 4th leg is used to compensate the neutral current. We may have unidirectional single switch boost converter, and these multi-level converters are also popular. Multi-level converters can be classified in this fashion: NPC, flying capacitor, hybrid converter, cascaded, and cascaded we may have H bridge which are connected in cascaded manner, and we can get the multi-level waveforms, multi-pulse and multi-level, and then the last classification is modular multi-level converters we can get. So, in this particular multi-level inverter we can get the reduced harmonics and TSD of the signal can be reduced. So, we have these 3 classification, we can go through it, and these are the few configurations, all 3 configurations which we have seen in the classification. So, let us go to the analysis of single phase unidirectional converter. So, in case of single phase unidirectional converter, as we have seen earlier, we have 3 devices which are used for DC-DC conversion, and simply we have used dart bridge rectifier over here. So, if you have not used this power factor correction unit DC-DC converter, then you may realize the capacitor is directly connected with the Darby rectifier and it will realize as a voltage step load, and many times if there is no control over there, the supply current will be peaky in nature. So, you can see here, if this DC-DC stage is not there, only Darby rectifier followed by capacitor is there, high peaky current is there and it has a THD of 70 to 80%. However, if you have connected this power factor correction unit, the supply current in perfectly in phase with the voltage. So, you can see the waveform without PFC and with PFC, and the utilization of power in the particular operations without PFC and with PFC. So, here we have the operations, we can switch on the PFC switch through control. So, inductor gets charged, and whenever we are providing off pulses to this switch, boost switch, the inductor releases energy to the capacitor, as well as fraction of energy it is going to the load. So, whenever the switch is on, the energy stored by the capacitor it is delivering to the load. However, when switch is off, stored energy in the inductor it is going to the capacitor, as well as some fraction of energy it is going to the load. So, this way we operate these boost converter, and here we have various equations. We can go through it, like when the switch is off. So, ID net current will go to the load as well as to the capacitor, and here we could find out the component is oscillating with the second cos 2 omega t. So, second harmonic ripple is inducting is there in the in the voltage which we are getting at the output side, as well as current which we are getting at the output side. It has to be addressed, because in case of single phase supply, this instantaneous power it is oscillating with the double of fundamental frequency. So, these ripple has to be addressed, and up to 10 to 15% these ripples are allowed, otherwise we need to redesign our system if the ripple are more than 10% or so. So, this way we can get the various equations for ripple and these powers, and then we could see here the operation under when we have applied this DC-DC stage, and we make the topology for charging the battery, unidirectional topology to charge the battery using dart bridge, and another stage as a DC-DC converter like boost converter. So, here you can see in first figure the voltage and current both are in phase and perfectly sinusoidal, right, and the total harmonic distortion at the input current. Whenever I am talking about input current, it means we are talking about grid current. So, input of the Darby rectifier current, the total harmonic distortion is 4.9, which is meeting the standard which we discussed in the introduction part. So, that is 4.9. So, thank you for participating in this lecture, which was on AC-DC converter with power factor corrections for EV charging. We explored various type of AC-DC converter topologies. We have classified, and we have also seen what are the challenges along with the power electronics based conversion devices when we are going to convert AC supply into DC. So, what would be the challenges? So, these challenges has to be addressed, and that we have seen in this lecture. I hope this session has provided you with valuable insights about the power factor corrections unit and deeper understanding of harmonics and other parameters. Please review the lecture material, feel free to post any question or comment in the forum, and thank you.